First talk in this session is by Juan Maldacena, and the title, okay, is slightly different. You can see the string size black holes. The idea is the same, but there is a slight change.
Okay, well, thank you for the invitation. I hope you can hear me. I'll be talking about string size black holes, or black holes at the string scale. So the talk will have a large component of review, where I would review the subject of black holes which have a string size and the connection or possible connection to highly excited string states. We'll discuss some aspects of these solutions in d = 4 and the Horowitz-Polchinski solution. And then discuss a certain 2D black hole, which is an exact string background based on an algebraic construction of an SL2 mod U1 COSAT. And finally, we'll review how you get a two-dimensional black hole from a large D black hole. And finally, I'll get to some work in progress that's almost finished with Yimin Chen, where we use this exact description plus that large D approximation we mentioned there to describe some aspects of stringy black holes. And we'll discuss the appearance of a large stringy thermal atmosphere as we turn to critical mass or temperature. And we'll also discuss how to compute the chaos exponent using those descriptions. Okay, so we will be considering a weakly coupled string theory. So the string coupling is very small. So such theories have two length scales. So one is the string length, and it's much larger than the Planck length. We will set the string scale to 1, and so G Newton will be for the G squared. And we will discuss mainly the bosonic string, but similar statements hold for the type 2 and heterotic superstrings. So first, let's discuss a highly excited free string. So such a string has a mass which, so in these units where alpha prime is 1, goes like square root of n, and an entropy that also goes like square root of n with a coefficient involving the total central charge, which is 24 for the bosonic string, so the central charge of, let's say, the transverse excitations. And so when you have such an excited string, so it's somewhat largish, so of this size. And the thermal ensemble is only well defined when the temperature is smaller than the hydron temperature. So here the inverse hydron temperature is 4 pi for this case. Okay, so the reason for that is that due to this linear relation between the entropy and the mass, the density of states also goes like the mass, and so it can be overwhelmed by the thermal factor in the density, by the Boltzmann factor, only in the case that beta is larger than beta h, or temperatures smaller than the hydron temperature. Now, if we turn now onto black holes, so black holes are well defined only if the Schwarzschild radius is much bigger than 1, and the leading order alpha prime corrections were computed in some papers in the 80s. And we can ask what happens as they approach the string size, or as their temperatures approach the hydron temperature. Now, it was long ago observed, first in this paper, that if you look at the entropy versus mass for a black hole, and you naively extrapolate that formula, of course, the formula for a black hole is only valid when the black hole is big enough, so that is for large enough entropies and masses, but you might naively extrapolate that formula. And also you can compare that with what you get for a free string, which again, you can only calculate for relatively low mass and entropy. So there we just get the linear relationship between the two. And if you naively extrapolate the two formulas, they cross at some point. And so you would think that perhaps the black hole would somehow turn over into this gas of free strings, because that would be the maximally entropic configuration. So this is just a qualitative statement, because we are extrapolating the formulas beyond their region of validity. Okay. So one question you can ask is where there is a smooth transition between the black holes and a highly excited string, or what kind of transition is there? And one motivation for trying to understand this transition is that in the string picture, the microstates are explicit. So we have an explicit description of microstates, but there is nothing similar to the black hole interior, at least not obviously. On the other hand, for black holes, there is some interior, but there are no obvious microstates. And so if we could understand the connection between these two pictures, and we would hopefully understand some of these issues better. So that's the general motivation for trying to understand string scale black holes. So now I'll review a few more things. So in d equal to 4, so in the particular case of black holes in 4 dimensions, Horowitz and Polchinski calculated the first correction to the free string answer. And they found that the entropy rises a little more with mass, so maybe they might connect smoothly. And they had some arguments that maybe they connect smoothly. But we don't really know. It could be that at some point in between, there is a second order transition, or maybe there is even a first order transition. So it's not really understood. So this I'm just listing some of the possibilities. For d much bigger than 4, we will, well, we will argue that physically we can continue this black hole side to temperatures, beyond to temperatures that are higher than the, a little bit higher than the higher than temperature, and we'll study in more detail what what the description is of this region. And Horowitz and Polchinski also argue that you can continue the free string description further than this crossing point. So now let me comment let me make some more comments on strings at finite temperatures. So when we consider string theory at finite temperatures, we compactify the Euclidean time direction. And then that's common when we want to describe a field theory at finite temperature. And then in the string theory context, there is a string that can wind the Euclidean time direction. So this is a particular winding mode, string winding mode. And that winding mode has a mass, well, we can write down an effective action for this winding mode, and it has a mass which is which goes to 0 when the temperature is equal to the higher than temperature. And for very large inverse temperatures, so beta very large, the mass is proportional to beta, is proportional to the size of the circle. So this correction comes from the Casimir energy of the excitations along the worldsheet of the string. But the important point here is that it becomes light when beta goes to beta h, and so we can, if beta is similar to beta h but slightly bigger, then we have some effective action for a light mode. So this mode becomes light, and we can write down an effective action. Now it turns out that this mode can have some self-interactions, and the most important self-interaction is the one due to gravity. And so you can write down an effective action of this form. So this leads to a simple action for the thermodynamics of strings, and it actually leads to an interesting solution in d equal to 4, which was found by Horowitz and Polchinski, the self-gravitating string solution. So it's a localized solution in 3 spatial dimensions. So the total space-time dimension is 4. So one dimension is a time circle. And it leads to a localized profile for the winding mode, and it describes a self-gravitating string in thermodynamic equilibrium. Its size decreases as the mass increases. Of course, this size should be much larger than 1 in order to trust the gravity approximation. And it breaks down when we get to masses or entropies of this order, of order 1 over g squared. So the description breaks down before we get to the point where it's supposed to turn into a black hole. And the temperature decreases as the mass increases. It has negative specific heat, so it's somewhat, in that sense, it's somewhat similar to a black hole. Now, one interesting property of this solution is that it is a classical solution of some classical equations. But however, it has a non-trivial entropy. So one can compute the entropy And the entropy comes from taking the derivative with respect to the classical action. The circle never shrinks, but there is some explicit dependence on the inverse temperature, or the size of the circle, and the mass of this mode. And because of that, there is a non-trivial contribution to the entropy, which you can compute, and you can derive this simple formula. And when you calculate it using their solution, you get an entropy which is linear in the mass. That would be like the free string result, and then there is some correction due to the self-interactions, and you can calculate all the numbers here properly. I'm not just writing them now. Now, so we saw that when we think about the string theory at finite temperature, there is this winding condensate that describes the string thermodynamics. But whenever we have any black hole, we also have a winding condensate. And this can be computed by thinking about a worldsheet that ends on the, so first we consider the Euclidean black hole, which has the topology of a cigar, if we consider the radial and Euclidean time directions. And then if we consider a worldsheet that wraps around the tip of the cigar and ends on a circle at this point, at this position R, we can then calculate the expectation value of the winding mode by calculating the area of the surface. And this gives something of the form e to the minus beta r minus r naught for the Schwarzschild metric, for example. So this is very tiny because in the regime where we can do this calculation, this is very small, but it's present for any black hole. And we can view this as a kind of thermal atmosphere of strings so among the excitations of the black hole, we have this thermal atmosphere of strings. One interesting point about this is that it gives a formally classical contribution to the entropy, formally of order 1 over g squared, but it's not really calculable to my knowledge. And since it's concentrated near the horizon, where, well, this simple approximation we were making here is not valid, and it was speculated in the past that maybe you can get the black hole entropy this way, but there are some arguments by double car, but I think they are not precise enough to give us a nice picture for the black hole entropy. So in conclusions, in d equal to 4, there might be an interpolating worldsheet conformal field theory that connects the black hole with the strings at finite temperature. Now we will review a particular black hole solution, which is exactly solvable in string theory as a worldsheet CFT. This is the two-dimensional black hole, which is based on certain Cosat model. So it's a two-dimensional metric. It is a quotient of a gauged, well, it is a gauged Wessel-Witten model, and it can be analyzed with the tools of Kac-Moody current algebras. So I'm not going to describe the details of this. The point is that we can analyze this for any size of the black hole. The metric can be written this way, has the geometry roughly of a cigar, and it has a two-dimensional dilaton, which has this form. So the coupling becomes very weak as we approach infinity. And so this metric is good for k much bigger than 1, but the algebraic description based on these tools is good for any k, even when the curvatures are of order string scale. Now, k, so you can think of k as setting the gradient of the dilaton far away, and therefore the central charge of the worldsheet CFT through a formula like this. I mean, k also appears in the expression for the currents, and that's its primary definition. But for the purposes of this talk, we'll think that k is defined through the gradient of the dilaton through this formula. And then one finds that the central charge of the two-dimensional field theory is 2, so that because we're in 2 dimensions, plus some correction coming from the gradient of the dilaton. And the radius of the circle at infinity is 2 pi times square root of k. Okay. Now, here, this is a peculiar black hole because if we think that we have a theory with a fixed central charge, then its temperature is fixed, and this was an odd feature, but this is a funny feature of this black hole. Now, in this particular case, one can calculate the winding condensate precisely. This is sometimes called the Fatayev-Samolotchikov duality to sign Liouville theory, but the bottom line is that it leads to an expression for the winding condensate where we have an expression roughly like this. It's convenient to think about this to consider a canonically normalized field. So the action for the winding mode has this form, but since phi varies, it's convenient to define a new field chi tilde, which has a canonical kinetic term. And this field chi tilde then decays in this way. So one important point that we see here is that this canonically normalized field decays at infinity only for k bigger than 3. So it's only in that case that we can think of this winding mode or this stringy halo to be localized near the horizon. If k is smaller than 3, then we should think of this stringy halo as coming in from infinity. So solution changes qualitatively at this value of k. And the contribution to the entropy from the winding condensate becomes infinite at k equal to 3. So there is some contribution to the entropy due to this winding condensate, which is not apparent in the geometric description, but is present when we describe this black hole exactly. And the expression for the entropy, as we've seen, involves an integral of the chi field, more precisely of this chi hat field. And so if it is growing at infinity, it will give us an infinite contribution. And it only gives us something finite when k is bigger than 3. So some conclusions about this is that the black hole picture and intuition are essentially good when k is bigger than 3 or when the temperature is bigger than square root of 3 times 2 pi, the inverse temperature. And when we approach this critical temperature, this winding condensate emerges and the atmosphere of strings extends to infinity and the entropy becomes infinite. It was suggested that we should interpret the solution for k less than 3 as a condensate of winding strings only with no black hole, but I personally don't know exactly how to think about this. But perhaps in all cases we have two alternative pictures. Now we'll review one more idea. So this is the idea that the large D Schwarzschild black hole, so Schwarzschild black hole in a large number of dimensions, leads to a theory near the horizon that consists of a sphere of times a two-dimensional black hole. So this is just the Euclidean black hole, the Schwarzschild metric for the Euclidean black hole. And the idea is to really define a new variable rho through this formula. And after we do this, then the R and T components of the metric, they become equal to the R and T components of that two-dimensional black hole that we talked about. And K becomes equal to twice R0 over D, so where R0 is the size of this D-dimensional black hole. And then the volume of the sphere goes like R to the D minus 2, and for large this is similar to R to the D minus 3, and that is proportional to cos squared, and this can be viewed as a two-dimensional dilaton, and that reproduces the formula for the two-dimensional dilaton of the two-dimensional black hole. So now we come to the thing we were doing with this. So we wanted to extend this large D observation to small k or stringy curvatures. So the curvature is high in two of the dimensions, so in the radial and time direction, and so as to make a more precise statement for Schwarzschild black holes in 26 of the or 10 dimensions in the approximation that, well, both 26 and 10 are much bigger than 1, for example. So this more precise description involves matching we have to find the relationship between this parameter k of the two-dimensional black hole and some parameter of the higher dimensional black hole. Now, an important point is that we have seen before, let me mention it here again, that we want to be in a regime where this k is of order 1, so that's when the temperature is of order the string scale, but that implies that R0 is of order d, and d was large, so the radius of the sphere is relatively large, and that means that we can treat the sphere to lead in order in alpha prime, so we can solve in some sense the theorem of the sphere, and in particular, we can calculate the central charge of we can approximate the sphere theory as a conformal field theory. It's not quite conformal, but we can approximate it as a conformal theory. So the sigma model whose target space is a sphere runs, I mean, it's not quite conformal, but we can approximate it as conformal for large radius. And in large number of dimensions, the central charge would be d-2, that's the dimensionality of the sphere. And then there is a correction from the curvature of the sphere that was computed by Zeitlin, and I think there was also a paper by Tratkin and Zeitlin. And when you do that, then you get this expression, because here we are just inserting the curvature of the sphere, which goes like 1 over the radius square of the sphere. And the sphere near the horizon has a size which is essentially R0. And then we can match this correction, this deficit that the sphere directions have with the excess that the cigar theory has above 2. And when we match these two, we find the precise relation between R0 and K. And we also had the relationship between beta and square root of K. And through this, we can find the relationship between beta and R0. And the only correction relative to the gravity formulas is this -2 here. And so once we have this, we can check we can check this against the large delimit of the alpha prime corrected black hole. So people had these papers, these two papers had computed the alpha prime corrections to black holes in string theory by considering the effect of higher order curvature corrections. And you can compare the corrections that they found. So they did the calculation for general dimension. So we can take the large delimit of their calculation and compare to what we get from the formulas I just showed you, and we get an agreement. So now something interesting is that as we vary the size of the horizon, we vary R0, we are varying K, this parameter of the cigar theory. So it gives us a more physical way of varying this parameter K. Now, something interesting, so okay, maybe I first should mention the following. So the Hagedorn temperature for string theory in flat space is when beta h is equal over 2 pi is equal to 2, and that corresponds to K equal to 4. So at this point, if we had, at this point, the thermal ensemble becomes ill-defined at infinity. Okay. However, in the near horizon region, this thermal, if we restrict just purely to the near horizon region, the thermal ensemble continues to be well-defined because the effective central charge of the sphere is a little smaller. So the string can oscillate in less direction, I mean, it has less degrees of freedom, and the thermal ensemble, at least in the near horizon region, continues to be well-defined. So interpret this as saying that the temperature of these black holes can rise above the Hagedorn temperature at infinity. And this is, of course, this you cannot do in the canonical ensemble because you would still have the problem at infinity. But we think that if you have an isolated black hole that is emitting Hawking radiation, its temperature can rise above the Hagedorn temperature in flat space. And locally near the horizon, it will be in some kind of approximate equilibrium. Of course, it will be radiating Hawking radiation to the region further away. So in other words, we have a solution where we have the horizon, and there is a near horizon region that can be described using the cigar theory. And in this region, the winding condensate is decreasing. And then eventually we have a region where the winding mode becomes tachyonic if we were dealing with the canonical ensemble. But if we are dealing with just a black hole that is evaporating, we just have radiation that is leaking outside. Okay, so what we are describing now, so all these words are describing this region of the diagram we have seen before. So we are talking about a black hole whose size became relatively small and smaller than the size at which the temperature is equal to the temperature, to the Hagedorn temperature. So we are describing essentially this region of the phase diagram of black holes. And the endpoint here is when this winding mode ceases to be normalizable even in the near horizon region, even in this cigar approximation. So at that point, we will not have even an approximate equilibrium, we think. And we cannot really describe what happens for lower masses. Maybe the black hole turns into string through some dynamical process that at least we don't know how to describe. Maybe someone figures out how to describe it. Now I'll finish with some other computation we can do with this description. So it's a calculation of the so-called chaos exponent. So we expect the dynamics of black holes is chaotic, and this can be made very concrete by looking at the special correlation function and out-of-time order correlator. And this receives an interesting contribution from a scattering process near the horizon. So by considering an out-of-time order correlator, we find that these out-of-time order correlators can be computed in terms of scattering amplitudes of particles that undergo scattering near the black hole horizon. So these are highly boosted particles in the near horizon region, and there is some graviton exchange whose effect grows when the time difference between the insertion of these two operators or these two excitations becomes larger and larger. So the out-of-time order correlator has a large correction. So this is the G-Newton correction, which grows exponentially with time, and the coefficient of the exponent is called the chaos exponent or quantum Lyapunov exponent. So in principle, you are supposed to compute the 4-point function. We did not calculate the 4-point function, but we just had a guess for what the exchange state is. And the guess is based by comparison with the flat space case, and we determine some of the quantum numbers by looking at their behavior and their boosts and so on. So this is just in terms of the algebraic description. We have some representations of SL2, and then we're acting with some of the SL2 currents. And we have some on-shell condition, which where L0 is the total conformal dimension. It has some contribution from these currents, which is S minus 2. Then there is some contribution from the values of the spin, which has this form, and of the SL2 spin. And then we should, when we do SL2 mod U1, we should just remove the U1 contribution, and that's this factor. So you can do this calculation, and then you get you can solve this equation for S. That gives us the spin of the exchange state, and you get that S minus 1, so it's 1 in the gravity approximation, because the spin of the graviton is 2. And then this is what the Lyapunov exponent becomes, and it decreases and becomes something smaller when k is equal to 3, which is the point up to which we can do the calculation. I mean, this calculation we can further extrapolate, and there is something interesting about the point where it crosses 0, but that doesn't correspond to the d-dimensional black hole. And one can check that the leading correction in 1/k matches what Schenker and Stanford had calculated previously. So in conclusions, we discussed how the large D approximation for Schwarzschild black holes leads to the cigar geometry. And the cigar geometry can have a string scale curvature, and we can still solve it. And we used it to explore the geometry of the black hole as we approach, and we argued we could surpass the Hagedorn temperature. But at the critical size or temperature, the black hole develops this large stringy halo over atmosphere, and we do not think that the black hole makes sense for lower masses. It probably turns over to some highly excited string state, but through a process that we don't know how to describe yet. And we also we computed this chaos exponent and found it to be non-zero at this point where the black hole ceases to make sense. So there are many questions for the future. So we could wonder whether this large D approximation can be used to study other string scale black holes, maybe black holes with Raman charges and so on. And we could also wonder what we can say about the gravitational picture for the microstates and the black hole interior, which was the original motivation, but I really haven't said anything about it. Okay, thank you.
Okay. Thank you very much for this very interesting talk. Are there any questions from the audience? Maybe I can start asking you one thing. So if there are,
yeah. There is a raised hand.
Please, sorry, Igor Volovich. I can see.
Thank you very much for the nice talk. If we apply the large D expansion to the ADS CFT homogeneous topography, what do we get?
Yeah, I don't know if, yeah. Well, I think it's an interesting question. We haven't thought about applying this to some interesting holographic examples. A case where maybe one gets something interesting might be the D0 brane black hole, which if you take the near horizon limit or certain decoupling limit becomes holographically dual to a matrix model. And perhaps in that case, so it's a black hole in 10 dimensions, and perhaps in that case you can use some interesting large D approximation. We have not studied it in detail.
Thank you.
And
another question, what is the relation of your limit with the Rindler metric?
With
usually near horizon we have the Rindler.
I think I did. Which metric?
Rindler.
Rindler. Oh, yes. Well, it is. Yeah. So what is the relationship? Maybe I should share again. Let me see. So we were discussing this. So we discussed that the geometry was similar to the cigar geometry. The Rindler metric arises when you go very near the tip of the cigar, right?
Yes.
That's the metric of flat space in Rindler coordinates. Now, in these situations that we are considering, where the curvature is of order string scale, the size of the string is comparable to the radius of curvature. So there is no region where you cannot really go to the Rindler approximation because the size of the string is so big that the region where the physics is well described by Rindler space is much smaller than the size of the string.
Okay, thank you very much.
Yeah, sure.
I ask a question.
Okay, please. There's another question by.
Hi, Juan.
Yeah, yes, please.
Very nice talk. Thank you. My question is, you speak about the two-dimensional cigar theory, and at the same time, it's embedded into some string theory. Yes, it's
exactly,
a string black hole, but it is string, as far as I remember, only at particular value of k, like 9/4. And you speak about other values. That means that you embed it into higher dimensional theory.
Yes. So let me just remind you how the cigar theory appears. So in your paper with your famous paper with Kostov and Kutasov, you considered a non-critical string theory which only had the cigar. So total central charge was 26 or 10 or something. So that's one case where you can consider the cigar theory. But the cigar theory also arises in other contexts in string theory. For example, it could arise in the near horizon geometry of a near extremal 5 brane. And in that case, you get the cigar, and then you also get the sphere and maybe some other dimensions. And so in that case, the K can be anything. So you can have, in that particular case, K has discrete integer values. In the case of the 5 ring, because there are some spheres, and the sphere is a Wessel-Witten model that has some integer values of K. And yet, this is yet another situation where the same thing arises. And here, the full conformal field theory consists of a sphere of d minus 2 dimensions times the cigar. And then we vary K continuously by changing the radius of the sphere.
Okay, thank you.
That's the idea.